Okay, welcome back. So I've got a handful of new stuff to go over today. We'll have a couple new rules for integration, but before I get to it, we've got some rules I need to go over for derivatives first. So we're going to be talking about inverse trigonometric functions. Inverse trigonometric functions, just like any other inverse function, change your input and your output. So normally we would say the sine at pi over 6 is equal to 1/2. If I took the inverse sine of 1/2, that would be asking what angle would give me a value of 1/2 for sine. My answer would be pi 6. So you can see my input and my output changed. If you see an inverse sine of something, you can take the sine of both sides in order to get rid of it. So if I take the sine of both sides right now, I'll end up with the sine of the inverse sine of 1/2. The sine of the inverse sine will cancel, and that leaves me with just 1/2 on the left side, equals whatever I do to the left side I have to do to the right side. So if I take the sine of the left side, then I have to take the sine of the right side, would be the sine at pi 6. Any questions just on the meaning for inverse trigonometric functions? Okay. So where this gets interesting is when we want to derive an inverse function. So if I want to derive an inverse trigonometric function specifically, then we can use chain rule to see what happens. So right now I've got the derivative of the inverse sine of x. So if my function y equals the inverse sine of x, then what I could do is take the sine of both sides to turn this into a problem that we can solve using our derivative rules that we already know. And then eventually solve for dy over dx would be the slope of my original y function. Hello Abby, hello Nikita, hello Andrew.
Sorry.
Oh, you're okay. So we are trying to find the derivative of an inverse trigonometric function. So I'm starting here. So y equals the arcsine or inverse sine of x. Both mean the same thing. So if y is the arcsine of x, then I can take the sine of both sides to get the sine of y equals x. And then derive normally with chain rule. If I do, this will be, if I derive sine, I get cosine. If I derive y, I get the derivative of y equals dx, or 1. Now, our goal is to solve for the derivative of y, because that'll give us the derivative of my original function, which is arcsine. So in order to solve for dy, I would have to divide by the cosine of y. So I could say dy equals dx over cosine y. Okay, so now the question is, what is the cosine of y? Well, right now we could say that the cosine of some angle y would be the same triangle, right triangle relationship as this line, where the sine of y was equal to x. Because the sine of an angle is equal to the opposite side divided by my hypotenuse. And our sine was equal to x over 1. Then I could set up a right triangle relationship where my angle is equal to y. Here's my angle y. The opposite side to y is equal to x. And my hypotenuse is 1. And then we could use this right triangle relationship to figure out what the cosine of this angle y would be. The cosine at that angle would be equal to my adjacent over hypotenuse side. So if I solve for this adjacent side, I could use Pythagorean's theorem, where x squared plus some side we don't know yet squared should equal 1 squared, and solve for c. So I could subtract x squared from both sides and get c squared equals 1 minus x squared, or c is equal to the square root of 1 minus x squared, which gives us this adjacent side. Then the cosine would be my adjacent over hypotenuse, or the square root of 1 minus x squared over 1. Any questions so far? Okay. So now that I've got a cosine that we can substitute for, anytime that I see a cosine y, I can substitute it for root 1 minus x squared. So if I do, here's root 1 minus x squared in where cosine y used to be, times dy equals dx. Again, my goal is to solve for dy, so I'm going to divide both sides by root 1 minus x squared, and I get our formula. The derivative of y, which was arcsine of x, is dx over root 1 minus x squared. dy is the derivative of my original function. So we could say that the derivative of arcsine x is equal to dx over root 1 minus x squared. Okay, any questions on anything from the first one? All right. We'll go over to the second one. If I want to do the same thing and solve for arctangent, I can take the tangent of both sides. This will give me the tangent of y equals x and derive it. The derivative of tangent is secant squared, and then with chain rule, that's secant squared y dy equals, on the right side, just dx. So this would be a triangle relationship where, because tangent is opposite over adjacent, my opposite side would be x and my adjacent side would be 1, x divided by 1. Okay, here's a right triangle relationship where our angle is y. My opposite side is x, and my adjacent side is 1. If we have that relationship, then we can solve for our missing angle, again using Pythagorean's theorem. X squared plus 1 squared is equal to c squared in this case, because c is my hypotenuse. Therefore, c would be equal to the square root of 1 plus x squared. Okay, then if I want to substitute for the secant squared of y, I can take this right triangle relationship and say secant would be hypotenuse over adjacent. That's 1 over cosine. Cosine is adjacent over hypotenuse. If I flip that, that's hypotenuse over adjacent. My hypotenuse is root 1 plus x squared. My adjacent side is 1. So now I can substitute. Anywhere where I see a secant squared y in this derivative, I can replace it with this. Okay, so the secant of y is this, and I need to square it to be secant squared. So if I square it, my square root will go away. So that leaves me with 1 plus x squared times dy equals dx. And if I want to solve for the dy, the derivative of my original function, then I can divide by this 1 plus x squared to get dx divided by 1 plus x squared is dy. I'm getting a Zoom notification, so I'm going to check this really quick. Okay. So this is the derivative of y, which was originally the arctangent of x. Should be equal to dx over 1 plus x squared, which gives us our formula. Any questions on what we did here? Can you guys still hear me?
Yes.
Yes.
Okay. So last one, we've done sine and tangent. So the last one I'm going to do is secant. Slightly more involved, although we're starting with the same idea. So y is the arcsecant of x. So in order to get rid of my arcsecant, I can take the secant of both sides. That gives me the secant of y is equal to x. If I want to derive it with chain rule, the derivative of secant is secant tangent, so that'll give me secant of y times tangent of y times with chain rule, the derivative of y equals dx. So in order to substitute for the secant and the tangent, I would have to set up a right triangle relationship where the secant of y is equal to x over 1. Secant y equals x over 1. Now, secant is the flip of cosine. Cosine is adjacent over hypotenuse. That means secant must be hypotenuse over adjacent. So here's a right triangle with an angle of y where my hypotenuse is x and my adjacent side is 1. Again, I can solve for the missing side. So that's c squared plus 1 squared equals x squared, or c squared equals x squared minus 1. Therefore, c is root x squared minus 1 for our opposite side. Okay, then I can substitute for secant. The secant of y is x over 1, or x. The tangent of y is opposite over adjacent, or root x squared minus 1 over 1. So here's my tangent. Secant and tangent. Okay, so we made our substitutions. Last step is to solve for dy. If I do, I can divide by everything else that's on the left side to get dy alone. So that gives me dx divided by x root x squared minus 1. Substitute for the derivative of y would be the derivative of arcsecant. And we've got our last formula. Okay, any questions on this one? All right, so I gave you equations for sine, secant, and tangent. I did not give any equations for cosine, cotangent, or cosecant. If you ever needed them, the derivative of arc cosine is the same thing, just with a negative sign. The derivative of arc cotangent is the same thing as tangent, but with a negative sign. And the derivative of cosecant is the same thing as arcsecant with a negative sign. So generally, because you can always pull that negative out, we don't use arc cosine, arc cotangent, or arc cosecant that often, because we can rewrite them as arc sine, arc tangent, or arc secant fairly easily. So if you know these three, and you can pull your negative outside the integral, then you should be able to solve all 6. So on its own, the derivative of an arc-trig function is not very common, but the integration of these trig functions is super common. And the reason why is because we've kind of hit a wall up to this point, where if we wanted to integrate something over something else, let me change my color here. If I wanted to integrate, we'll say u squared plus 1. So this is u over u squared plus 1. My derivative of this bottom part would have to be the right power to be on top. By doing these rules backwards, so that the integration of dx over 1 minus x squared would equal arc sine of x. My powers don't have to be 1 power less than the bottom on top. My powers can be 1 power less than half of what's on bottom. So what I mean by that is this is a u squared. Instead of having u to the first power on top, I now have u to the 0 power on top. That's half of 2 minus 1. So this opens up a lot more functions that we could possibly integrate. Okay, now these rules don't quite match what I had over here. So I'm going to do one of these just to show you that it works. So we'll jump back in here. So what I want to do is I want to integrate a general form for my right side of this equation. So that's u prime over u root u squared minus a squared. I'm making this even more general than what I had originally on the right side. So that I have any real number a and any function u. Okay, so our rule says this should be 1 over a times arctangent of u over a plus c. I'm going to prove it by taking this and deriving it. If this is true, I should end up with this left side of the equation. So I've got 1 over a times the arctangent of u over a plus c. Okay, so if I derive arctangent of something, I should get dx over x root x squared minus 1. Right now my inside part of this function though is u over a. So my derivative of my inside function would look like this. So I've got 1 over a as a constant, so I can pull that out. Times the derivative would equal this, where x is my angle. So the derivative of this inside part would be u prime times 1 over a. One over a times u prime on top over my inside part of this angle, u over a, times the square root of my angle squared, u over a squared, minus 1. Okay, so if I rewrite this, I should get back to this, is my hope. Okay, so if I do, this is 1 over a squared. On this side I've got u over a and the square root of u squared over a squared minus 1. Okay, where if I multiply this in, this will be 1 over a times u prime over, if I multiply 1a through, then these a's will start to cancel. Okay, so I multiplied 1a here, and I had 1a on bottom. If I do that again into this square root, so 1 over a is the same thing as 1 over root a squared. Oh. Okay, I've just lost Skype, and I'm losing Zoom. Okay. Okay, I've got Zoom back up, and Skype's going back up. Hello, welcome back.
What happened?
That was my end. My internet just spiked.
Oh,
All right. What's the last thing you guys saw from Skype? So I'd zoom on a little bit longer. Are you guys caught
the
up to this step?
tan thing? The U over something.
Or something. Okay, so way back here at U over A.
Oh yeah.
Okay, so what I'm going to do is I'm going to derive 1 over A times the arctangent U over A plus C, and my hope is that I will get back to this, so that I will prove my rule. So if I do, this 1 over A is a constant, so that's going to stay the same. And then if I derive the arctangent of something, I'll get the derivative of my
Mr.
angle.
Brandon,
Yes.
I can't see your screen.
You can't see my screen.
Yeah.
Okay, I'm sharing.
Okay, now it works. Yeah.
Okay, you can see it now. Cool. Okay, so if I derive this, my 1 over A is a constant, so that's going to stay the same. The derivative of arctangent of an angle is the derivative of the angle over the angle times root angle squared minus 1. So if I plug that in, this is the derivative of the angle. Derivative of U over A is U prime over A. Over my angle, U over A, times the square root of my angle squared, U over A squared minus 1. Okay, this 1 over A is the same thing as multiplying the entire fraction by 1 over A. So if I pull that out, this will be 1 over A squared on the outside. Okay, I can multiply one of these A's on the bottom times this A on the bottom, and that would cancel. The other one is the same thing as, let me rewrite this, this is 1 over root A squared, which means I can multiply it into this root. Okay, if I do, this will be A squared times U squared over A squared will cancel. And then A squared times 1 is A squared. So that leaves me with U prime over U root U squared minus A squared. Which is what we had originally. U prime over U root U squared minus A squared. Okay, all of that is to say these rules are true. So some patterns really quick to help you out. Arcsine is the only function that does not end up with a 1 over A in front. Arctangent and arcsecant both have 1 over A's in front. And then all of them have U over A's for their angle. Okay, any questions on our rules? Okay, so we'll use them. So if I wanted to derive this function first, so I'm deriving the arcsine of 2x to the 5th power. Well, the derivative of arcsine of x, we said was dx over root 1 minus x squared. So if I derive this, where I have an angle instead, my angle is 2x to the 5th power, so the derivative of my angle is 10x to the 4th power dx over the square root of 1 minus my angle, that's 2x to the 5th power squared. which is the same thing as 10x to the fourth power dx over the square root of 1 minus 2 squared is 4, and x to the fifth power times x to the fifth power is x to the 10th power, or 10x to the fourth power dx over root 1 minus 4x to the 10th power. Okay, so now I just gotta find that. Okay, that was fast. Our first one matches, but this one they derived regular sine instead of arcsine. This one they did not square the bottom part. And this one they don't have a square root. Okay, here's one more. So if I wanted to differentiate the square root of arctangent of 4x, then I could say my inside function, u, is the arctangent of 4x to the fourth power. That means my original function y is equal to the square root of u, or u to the 1/2 power. If I derive u to the 1/2 power, I'll get 1/2 u to the negative 1/2 power du with power rule. So that gives me my u, which is arctangent of 4x to the fourth power. If I derive it, would give me the derivative of my angle on top, which is 16x cubed dx, over 1 plus u squared. That's my arctangent formula. So this is the derivative of arctangent of x is equal to dx over 1 plus x squared. So if I say this is an angle, arctangent of an angle is the derivative of my angle over 1 plus my angle squared, and substitute that in, I'll get this. Derivative of my angle is 16x cubed dx, and then my angle is 4x to the fourth. So I've just substituted in. Okay, now anytime I see a u, I'm going to replace that with the arctangent of 4x to the fourth power. Okay, so here's u to the negative 1/2 power. That's 1 over root u. Would be 1 over the square root of u, which is arctangent for x to the fourth power. I'll do this in another color. Okay, so here's green for u, is arctangent 4x to the fourth power, so I've substituted that in. U to the negative 1/2 again is 1 over square root u. 1 over root u. Okay, then my derivative of u, which we'll do in 2 lines. My derivative of u is 16x cubed dx over 1 plus 4x to the fourth power squared. That stayed on the top of the fraction for my y prime, so I'm going to put that here on top. So all of this is the derivative of u. Now I've got a fraction divided by a fraction, 16x cubed dx over 1 plus 4x to the fourth power squared, over 2 root arctangent 4x to the fourth power over 1. So if I divide a fraction by a fraction, I can flip and multiply. So if I flip this bottom part, I'll end up with 1 over everything that we had on bottom. And then I can multiply straight across. Okay, I've got a 2 and a 16 that can cancel, so that leaves me with 8x cubed dx on top. 8x cubed dx on top. And then on bottom, I've got 1 plus 16x to the 8th power, and that's 4x to the 4th power squared. 4 squared is 16, x to the 4th squared is 8x to the 8th power, times the square root of arctangent 4x to the 4th power. Okay, any questions on this one? Okay. So I've got one more I'm going to flash, and then we'll try one together. So I've got the arcsecant of the fourth root of x cubed plus 4. So I could say that u is my inside part. The fourth root of x cubed plus 4 is x cubed plus 4 to the 1/4 power. That is this rule. X to the m over n is the nth root of x to the mth power. So I've rewritten from this form to a form that we can use power rule for differentiation for. Okay, so that gives me this. If u is x cubed plus 4 to the 1/4 power, then the derivative of u is 1/4 of x cubed plus 4 to the negative 3/4 power. That's 1/4 minus 1. Or 1/4 minus 4 over 4 is negative 3/4 for my power. Times the derivative of my inside function. My inside function was x cubed plus 4, so my derivative of the inside part is 3x squared dx. Okay, now if I substitute in the derivative of arcsecant, so the derivative of, arcsecant of an angle is the derivative of the angle over the angle times the square root of the angle squared minus 1. So if we plug that in, this will be the derivative of u, which is my angle, over u root u squared minus 1. Okay, now I can just substitute in. So here's my du, and I'm going to substitute that for du. And here's my u. I'm going to substitute that everywhere I see a u. Okay, and that leaves me with this. Substituting for du puts all of this at the top. Substituting in for u gives me an x cubed plus 4 to the 1/4 power. Here, oops, can't see that. White on white. Here and here. Okay, then we can simplify to get our answer, which I haven't done yet, so let me go ahead and simplify right now. This is x cubed plus 4 to the negative 3/4 power, which means I can move 3/4 of that on the bottom. So that'll give me y prime is equal to, I've got a 1/4. We'll move the 4 to the bottom of the fraction. On top, the only thing I have left is 3x squared dx. 3x squared dx. This negative exponent means I can move this x cubed plus 4 to the bottom. So this is x cubed plus 4 to the positive 3/4 power. If I move it to the bottom, that gets rid of the negative sign of the power. Okay, times x cubed plus 4 to the positive 1/4 power, which I had originally on bottom, times the square root of x cubed plus 4 to the 1/4 power squared would give me 2/4 minus 1. Okay, x cubed plus 4 to the 3/4 times x cubed plus 4 to the 1/4. If I have the same base and I'm multiplying, then I can add the powers. So this will be 3/4 plus 1/4 is 1. Gives me 3x squared dx over 4 times x cubed plus 4 to the first power times the square root of x cubed plus 4 to the 2/4 power is the same thing as the 1/2 power, which is another square root if I wanted to write it, but I think I'll leave that like this for now. X cubed plus 4 to the 1/2 power minus 1. Any questions on what we did for number 7? Okay, I've got someone on Zoom speaking. Unfortunately, I can't hear, so let me see if there's anything I can do. Some of the homework is multiple choice, so you'll have to simplify in order to match. But if it's a free response question like this, then you don't need to simplify, but I do need to see your final substitution, which means you'd be okay at this step. But you can't leave your answer in terms of u. It has to be in terms of x, or whatever the original variable was. Okay, good question. Anything else? Okay, so let's try one. We'll go ahead and do this one. So I'll write on our new rule up here because we probably don't have them memorized yet. I've got the derivative in terms of theta of the arctangent of theta would be equal to d theta over 1 plus theta squared. Okay, so if I said y was equal to the arctangent of 5x cubed plus 1 squared, what should my u be if I want to do a u substitution? Okay, 5x cubed plus 1. I might even include the squared for now. So u is 5x cubed plus 1 squared. So I want everything that's a part of that angle. Then what would the derivative of this be?
15x squared.
Okay, so that's my chain rule part. So I've got something squared will give me
2 times 15x squared.
Okay,
Over 2 times 5x cubed plus 1.
there we go.
15x squared.
Perfect. Times 15x squared. I've thrown a dx in here just in case x isn't just x. So that'll allow us to give a more general rule. I'm going to rewrite that 15 because that looks a little weird, but 15x squared. Okay. And then anything in the first power, you don't have to write the 1. Any questions on the derivative of u? Okay, so we go to the chain rule. So that gives me my original problem now. After I substitute for u, looks like this. Y is equal to the arctangent of u. So the derivative of y then should equal the derivative of u, which would be u prime, over, if I follow my formula, 1 plus u squared. 1 plus u squared. And now all I have to do is substitute. Okay, so making that substitution, anytime I see a u prime, I'm going to replace it with all of this. Oops, u prime. And then anytime that I see a u, I'm going to replace that with 5x cubed plus 1 squared. So what should this be for y prime? Okay, next step, we just need to substitute. Okay. I'm going to go ahead and do one step here. So let's do 10x cubed plus 2, because I'm just running out of space, times 15x squared dx. Oh, okay, it looks like our answers multiplied that out differently, so I'm going to go ahead and backtrack. Our answers have 5x cubed plus 1 alone, so I'm going to leave that. So this will be 2 times 15x squared is 30x squared times 5x cubed plus 1 times dx. Okay, then on bottom I've got 1 plus u squared, so that's 1 plus what?
5x cubed plus 1 to the 4th.
Perfect. 5x cubed plus 1 to the 4th power. That was 5x cubed plus 1 squared squared. Okay. So it looks like we're simplified enough that we can match to a multiple choice. So, which answer is correct?
D.
Okay, D is right. Go through each one really quick. This one just derived tangent, not arctangent, so not A. This one, our power is off here. And this one has a square root that we don't need. Okay, then working backwards, we wanted to integrate. So right now I've got square root of a constant minus my functions. That tells me this is a sine, which there's only one answer that is sine, so we've already got it. But right now, if I integrate du over the square root of a squared minus u squared, I should get the arcsine of u over a plus c. Was our rule for integration? Right now, u is x, and a is 1. So here's u and a. So that means on top, I should have the derivative of u. If u is x, then that's the derivative of x. That's u prime. And we match. Okay, same thing here. If I integrate du over u root u squared minus a squared, then I'll get 1 over a arcsecant u over a plus c. So here's my general rule. Right now x is t, and a is 2, because this would be a squared. So that means my answer should be 1 over 2 times the arcsecant of my u, which is t, over a plus c, which matches d. Okay, without the guides. So my first clue that this is an arctrig function is that if I try to make a u-substitution for the inside part, u equals e to the 8x minus 16, u prime then would be 8 e to the 8x minus 16, which is not the right power for what I have on top. So we can't do a normal u-substitution. So the next thing I'm going to try is to say, well, if this was an arctrig function, then this could be u squared minus a squared in here, which means u squared would be equal to e to the 8x. And if that's true, then u would be e to the 4x instead. So we'll try that. If u is e to the 4x, and this is an arctrig function, then this 16 is really a squared. A squared equals 16. That means a is equal to 4. Okay, with my arcsecant function, the integral of u prime over u root u squared minus a squared is equal to 1 over a arcsecant of u over a plus c. We can substitute. Okay, so I've got u is e to the fourth, e to the 4x. U prime then would be e to the 4x times 4, or 4 e to the 4x dx, which is what I have on top. So this is all u prime. So I've got the integral of u prime now over u is e to the 4x, and that is what I have on the outside here, u times square root of u squared minus a squared. And we're in the perfect form for our arcsecant function. So my answer should be 1 over a times the arcsecant of u over a plus c. And now I just need to substitute. A is 4, so this is 1 over 4 times the arcsecant of, let me write that because that looks like an integral, arcsecant of u, which is e to the 4x, e to the 4x, over a, 4, plus c. Okay, any questions on this one? All right, that was a lot for one day. So I've got a bunch of practice problems that we'll try this time, which I'll be posting to WeChat right now.
What do they do?
I don't actually remember. Let me double check. Okay, this is last week. We had this one from integration part 2, which was due today. Okay, so this one should be due on Wednesday then.
That's a lot of questions. 25.
It is, but it's kind of leveled. So let me jump in here. So sort of like what we did when we introduced U-Substitution for the first time. Where you've got a bunch of multiple choice questions where I'm giving you most of the answer, and you're just kind of matching. And we slowly build up to you actually solving on your own. Okay, so here's the homework. You can see the first couple questions, which take up a whole page because I had to throw all the multiple choice in here for both the unsimplified and simplified forms. I've kind of done most of the work for you and you're just matching. And we slowly build from matching to actually doing U-substitution and then matching and then doing it as a free response. So I've got that for derivatives. 4 questions, slowly building up multiple choice, and then 4 questions you're doing on your own. And then for integration as well. So 4 questions, multiple choice building up, and then 4 questions on your own. And then the same thing for our arc trig functions. Until eventually we've got it and we've got bounds. So it's 25 questions, but my hope is this won't take as long as you would think, because 8 of those 25 questions are multiple choice. I'm just kind of building you up to another 8 questions that aren't, and then the handful of questions we actually want to test today.
Can we maybe finish this on Wednesday midnight or something?
Yeah, Wednesday midnight's fine.
Alright.
So this is due at when?
Wednesday at midnight?
Okay.
Okay, let me double check, make sure I posted to WeChat, and then we're good to go. Okay, I can't tell from here, so I'm going to re-upload just in case.